Hello everyone, and thank you for making it until here. My name is Wendi, and I'm a functional safety engineer at Woven by Toyota in the global safety and quality line of business. And today I want to talk about an emerging opportunity, bringing functional safety into the open source world of LLVM, and what it could look like to qualify LLVM as a safety-relevant tool. But before, I would like to give you two warnings. The first one, I'm sorry, I don't know why I cannot. Okay. So the first one is that I have a voice condition, which means that my voice may break up or sound strained or breathy during the presentation. So thank you for your patience. And the second one is that during the presentation, I will mention many terms that may be unknown or weird, obscure for you, and actually I will not explain them because we don't have enough time. Okay? I will display them just because they are very important in the context of functional safety. I prepared some annexes, so maybe later you will be able to check them. If you have questions, you can also contact me, no problem. Okay, well, some specific sectors of economy, such as the medical sector, defense, energy, transportation, space, gas and oil, and also amusement rights, are considered safety critical. Safety critical means that the consequences of a failure or malfunction, meaning a problem in functioning, can lead to significant risks, including serious injury, environmental damage, or loss of life. In general, we refer to product safety as a product's ability to be used as intended without resulting in significant risks. Nevertheless, there are several sub-elements of safety. For example, mechanical safety, electrical safety, crash safety, thermal safety. And today I will mention one that is functional safety, specific to electrical, electronic, and programmable electronic systems. So, even with the best design efforts, systems may not be perfect. We may still have some scenarios, use cases, or conditions where things can go wrong. And the level of risk to have a defect is never zero. With functional safety, we reduce the probability of risk to an acceptable level by preventing, detecting, and handling hardware defects and software bugs. One example of a hardware defect would be a steering angle sensor stuck at 0 that could lead to the steering being locked while driving. And an example of software bug could be a buffer overflow in the perception stack of an autonomous driving system, leading to incorrect detection or classification of the objects like pedestrians or other vehicles in the environment. So, where failures could have catastrophic consequences, the prescribed acceptable level is 10 to the minus 9 per hour. So that is 1 in a billion probability. So we want to reduce to that. So how to design a system with such a low probability of a dangerous event occurring? Well, some international agencies and industry groups developed safety standards as a solution. Each safety critical industry has one or several safety standards with prescribed sets of requirements, guidelines, and good engineering practices to reduce the probability of risk occurring and to ensure safety. In automotive, we have ISO 26262 for functional safety. And all these safety standards have something in common. They require confidence in the development process, including systems, hardware, and software, and with many sub-processes such as specification, design, implementation, testing, and everything that you have to do at each level. So that's where software tools and compilers come in. Software development tools like compilers support the activities and tasks in those rigorous development processes that I mentioned before, and hence they support functional safety. I will give you an example. Maybe we have people from OEMs here. So just like tools used in a car factory, imagine a robotic arm on an assembly line that installs airbags. If that robot is misconfigured or the calibration is off, it might install the airbag incorrectly. So even if the airbag itself is perfectly designed. So there is difference between these systems that we develop with tools and the tools themselves. Is that the systems are inside the car and the software tools are not. So for systems, hardware and software, we want to make them safe. But that is not the case for software tools. For software tools, what we want is to have confidence in their use. And confidence in their use can be summarized in these three main ideas. To follow a structured evidence-based process for tool development, evaluating the level of confidence that the software tool can be used properly in a safety-related context. And when higher confidence is necessary, ensure its reliability and correct functioning. So I will show you how it is usually done in practice by a tool provider. I will not mention what happens on the user side. Let's see only the point of view of a tool provider. So the first step is defining the tool, actually. This is about making the tool understandable and predictable. And it's usually given in user manuals and release notes, as simple as that. For example, what does it do? Let's say it's compile C, C++ source code into target-specific machine code, and you define what those targets are. What are its inputs and outputs? Well, inputs could be source files, build configurations, toolchain components, and so on. And the outputs, object files, executables or libraries, assembly or IR, debug symbols, etc. Maybe some log files. What are the suitable execution environments or host platforms? Maybe Unix, Linux, Windows, Mac OS, etc. But what version? What should be the minimum version of the host platforms? What's its expected behavior, even under abnormal conditions? So what are the diagnostics in that tool? What are the error and warning messages? Are they well defined? Are they known? Etc. Next, we perform a kind of simplified risk analysis to assess tool malfunctions and assign a tool confidence level, reflecting the level of assurance required to use the tool without introducing or missing dangerous defects. So for each use case, you ask yourself 3 questions. What could go wrong? How severe would the impact be? How can we detect it or prevent it? For example, during installation, the compiler or a library included in the package may be corrupted during installation. Hence, programs and libraries produced using the toolchain may behave unexpectedly or crash. What could be a detection or a prevention measure? Well, maybe to compare the local install checksum against the provided checksum. That's just one example. During configuration, what could go wrong? Maybe the driver passes incorrect flag to downstream tools. And then the compiler program may not meet the user's performance or size needs, or it may contain instructions that are not interpretable in runtime environment and crash at runtime. Do we think that this is detectable or preventable without putting too much burden on the user side, that they have to thoroughly test the output, the executable file? Is that possible? Maybe yes, maybe not. We can find a solution. And during execution, another example, the object file emitter emits incorrect instructions, control flow structures, global values. Then the object file may not behave as expected or crash. Can this be fully detected or prevented? Maybe yes, maybe not. You need to think about that when you do this evaluation. Okay? And in the end, you have this tool confidence level, which can be high confidence, medium confidence, low confidence. There are 3 levels in ISO 2626. So then, the third step, when your confidence is not enough, or not high enough, you have to do a qualification. This means that you need to provide additional assurance that the tool behaves as expected. These could involve redefining, redesigning, or enhancing the tool's design. It can involve using validation suites or assess its development process with an audit. So here the idea is to reduce uncertainty by adding structure and traceable evidence to how the tool is built and how it behaves. The last step, because in the end, confidence in the use of the tool is about how users apply it, you document the usage constraints, assumptions, limitations resulting from the previous steps. So this helps ensure that the tool will be used properly and consistently, especially in edge cases. So these 4 steps that I presented, all of them are especially important for compilers, where errors can be subtle and hard to detect. AMI's compilation might not show up in testing of the output file, not always. And coding guidelines don't protect against compiler faults. So the compiler itself must be trustworthy. And also, especially in those cases that I mentioned, which are autonomous driving, assisted driving, where it is very, very difficult to test all the scenarios. So this is why there is an interest in qualifying compilers like LLVM in safety critical domains. Which brings us to this question. Could we build a shared open qualification path for LLVM that benefits both industry and the community? And this is an open question, and I will refine this question with two other open questions. So, could we explore the interest in qualifying LLVM upstream? And if we did, could this grow into something more than just safety compliance? Because I think that people outside of safety critical industries could also benefit from having a higher quality compiler. So this really can be more than safety compliance. Well, but there are real challenges. I will mention three. First, of course, LLVM is large, evolving, and highly configurable. LLVM project gets hundreds of commits per day. There are hundreds of bugs. Maybe most of them are corrected very, very fast, like maybe the same day. But it's changing fast. So how to manage this? It means that qualification targets will need to be scoped very carefully. The version, what backend, what front-end, what feature set. The second one, and please don't shoot me, especially the LLVM developers, open source workflows aren't always designed with safety documentation or traceability in mind. So we need to enhance how quality evidence is recorded and shared. It's about formalizing the quality evidence. And finally, today's landscape is fragmented. Many vendors have already qualified their LLVM-based compilers privately, and these efforts are very costly, duplicated, and non-collaboratively. So we could do better together. One way to move forward could be to form a safety group, similar to LLVM's existing security group. But it would not enforce process. It would support structured safety discussions. And for example, it could help with contributing with safety relevant specifications, identifying and filling some testing gaps, if any, tracking down known issues with safety impact, coordinating upstream changes that improve qualifiability, and maybe also serving as a contact point for tool vendors working towards ISO 26262 or EN 5128 for the railways industry or similar goals. This group could create structure without too much bureaucracy and value without giving more constraints to the developers. The second idea is, of course, how this could lead to a collaborative qualification effort, thinking that shared effort brings shared benefit, that transparency increases trust and enables reuse. We could develop reusable safety arguments, traceable documentation, and testing strategies with compiler engineers. But we would need to scale up incrementally. We cannot do everything at once, starting small and growing over time. And there are some precedents, actually. For example, efforts around the Linux kernel, the Concert compiler, the Rust Ferrocene toolchain, and why not, LLVM could be next. Ultimately, qualification isn't just about checking boxes or passing audits. This is really about building deeper trust in how the compiler behaves. It's about making LLVM a dependable foundation, even in the most demanding environments that I already mentioned. And the same practices that help us meet safety standards also make LLVM more reliable and robust for everyone. So this is not just a safety initiative, it's a quality initiative. And it could strengthen LLVM's role across industries. Thank you.
Any questions? Thank you for the talk. You have a strong voice. I think we somehow need a job, so we are funded by our own companies. So what are your plans to build a safety group if, like, we're working on our own platform, our own backend? What do you
I need
see?
to talk with your boss. Yeah. Yes, I think that, well, I'm the person proposing this today. And if I need to talk with your boss, really, I would. Because we need to convince people from several companies, especially I'm thinking about OEMs and tier ones. They should be interested in this, really. What is your company, sorry?
No, I'm just asking a random question.
No, but I'm just curious.
I'm from NVIDIA.
Okay, I see. Well, you have some safety engineers at NVIDIA, yeah. And yeah, you use compilers and you contribute to LLVM, so probably you would be interested. So let me go back to this slide. This is really a call for the industry to come and create this safety group together. My hope would be that they will pay you to do this. They will pay us to do this. Yeah. That is my hope. And maybe, hey, I don't know, I'm just having some ideas here. Why not with funding from other companies? I don't know. I don't have a definitive solution for this, but let me talk to your manager.
Any other questions?
Thank you for your talk. So if I'm a junior developer and I'm just starting off working on LLVM, what does this process, or a version of this process, what would you imagine that looks like if I'm just starting off and I want to commit basic changes? How would they interface? Would this impact them at all? And what would they expect from this?
What I would expect from someone who is starting. Well, this part about the open qualification. So this is a a call for the compiler engineers. So the other one was for the industry and for safety engineers. And you're telling me this is not an expert in compilers. Well, here probably we would need people that know the intricacies of the compiler, that know where things can fail. Does someone who is just starting know everything about this? Maybe not. But they can contribute with improving the testing, for example. They can contribute in identifying maybe things that could be strengthened or hardened. I think they will be able to contribute in that aspects. Yeah.
Thanks for the talk. I'll choose my words carefully because in case you need to speak to my manager, he's sitting behind me. Do you think there's a good entity or foundation under which such a collaboration could occur? Do you have anyone in particular entity in mind, or do you think that's still up for discussion in terms of a collaboration between companies for LLVM safety story?
Of course, there is the LLVM Foundation. Why not? Let's create an RFC and see what people think about it. Yeah.
Thank you for the call, for the presentation. It's really good. I think you touched upon something that is really important. So I do have a background in safety and security. But more than just the compiler, right? We as a society are moving into this new world in which we are sharing physical space with machines, right? So we start having drones and vehicles around us, machines, and safety is extremely important. Even a very small machine, a single defect in the tool chain in any place, if it triggers any misbehavior and the machine just physically moves to the side and gets in the way of another machine, this is going to have safety implications. So
maybe just 1 millimeter.
Yeah, exactly.
Could be sufficient.
So this is something that I have to deal with every day. Usually, security engineers, they see a problem in the code and they say, "Oh, it's not a security problem, so let it go." And the main, there is a bigger problem that I see is that this needs some kind of a legal framework, I guess, or some push from somewhere, because if people or if companies don't see the need or the push, they don't do anything. And also there is the so I think it's a challenge. Also, right now, we don't have standards, right? So for security, if you find a problem in the source code, people start asking, does this have any impact on confidentiality or availability or blah, blah, blah? And you have scoring systems for security, but for safety, there is nothing, right? I believe that from now on, every single defect in a software system should be treated as like priority. Like there is no like confidentiality or whatever. It doesn't matter anymore. Like any single defect, especially for a compiler, should be fixed and should have like some.
Should be auditable.
It should be like treated as a critical issue. That's the way I see it. But the problem is there is no standard, no push.
Well, the standards are there. What we are lacking, maybe, it's the enforcement.
Yeah, exactly. Well, yes, maybe that's the case.
Well, and not in all industries. If you see how a plane is developed, they have certifications, very strong certifications. I have never worked in that industry, so I don't know about the software tools part. But in railways, I have worked in railways, and they also have safety standards, and they do tool qualification. And actually, they have certifications. They really enforce the safety standards. But in the automotive industry, that is not happening yet.
Yeah, exactly. So I'm talking more about like, so for security, if you find an issue, you get a CV ID, right? So there is some, you can trace the issue, but for safety, like 90% of the code under like your code, private companies build something, but it's running on top of open source software, right? Who is checking this open source software? If I find an issue on a compiler or well, let's say some other system that's dependency for my system,
what I can say is that it is very difficult for the users, for the final user, to do it. They cannot check all tools. As I mentioned earlier to someone here, an OEM will use not 1, not 10, but 200 tools, plus many scripts and jobs in CI/CD/CT, and they cannot manage all the risks. That is impossible. It's same as with the embedded systems. Now that we are moving towards SDV, that we are moving towards this autonomous driving, we will not be able to even imagine all the catastrophic scenarios, all the significant risks that they will involve. So at least my proposal today is to help these OEMs and tier 1s with having more trust in the software tools that they use to build embedded systems.
Thank you.
All right, thank you so much. So that brings us to the end of the day. We're actually a few minutes over, but our executive director of the executive director of the LLM Foundation, Tanya Latner, is going to give us some closing remarks.